Hey, physics fans, let's do this together. Let's do this linearization together. And yes, I said physics fans. I promised myself that I would never say it, but I guess it feels right. Anyway, let's do this together. So this is the linearization table. This is something similar to what you're going to be looking at the lab WPR. Let's do this. You experimentally determine the drag coefficient C. Remember the verbiage. Determine the drag coefficient C. So that means that if it's determining something, that is going to be your objective quantity. That's what you're going to be solving for. By releasing circular coffee filters of varying diameters. Varying diameters. It's changing. Varying. That's going to be your independent variable. If it's changing or varying, it's going to be your independent variable, because if you change those things, that's going to affect your dependent variable, and your dependent variable is the thing that you're measuring. So you're measuring the filter's terminal velocity. So that is going to be your dependent variable. Then it says where M is the mass of the coffee filter, check. G is the acceleration due to gravity, and density of air is, you're given the density of air, and mass of M of each coffee filter is the same. So, noticing mass doesn't change, density doesn't change, acceleration due to gravity doesn't change. So that means that M, G, and density are going to be your control variables because they don't change. Okay? It's important to understand that. If it says they're not changing, or they're constant, like for example, acceleration due to gravity is constant, then you know that those are control variables. Now, do not get confused with the other labs, because in the other labs you were solving for the acceleration due to gravity. That was the thing that you were determining. In this scenario, what you're solving for is the drag coefficient, not the acceleration due to gravity. And here we are assuming the acceleration due to gravity is already given. Okay? So let's go through this problem. Identify the fundamental physics, second law with drag, got that. Apply the physics, got that. We are going to be given step 1 and step 2. Now, what you need to identify is step 3 through 8. So let's do this. We already said that when it comes to the independent variable is D, because D is varying, it's changing. Remember, dependent variable is the thing that you're affecting by changing the diameter. It's the thing that you're measuring. Remember those words. And what you're measuring is terminal velocity. So now you want to rearrange the equation to fit as such the linear equation. So the linear equation goes as y equals the slope times x plus b. In this situation, we don't have any intercept, so that goes to 0. But now we can identify that v is y, because we identified that as the dependent variable. In a linear equation, just to make sure that you understand, the linear equation, y is the dependent variable and x is the independent variable. Understanding this, that means the velocity goes in the y. Then we have the slope. So we go parenthesis, so the square root of 8 times mass times g over pi times c times density, close parenthesis. So notice that I have the mass, gravity, pi, c, and density. Anything that is constant anything that is constant and like you can include on the slope, do it. The only thing that should not be included on the slope is the x part, and that would be the square root of 1 over d squared. Notice d squared right here. I just literally separated them because d is my independent variable, but I am putting it in exactly the same form as the equation is offering me here. Okay? So now that you have separated the y, the slope, and the x, the dependent and independent quantities, like how exactly is it in your line equation? So dependent quantity, because that is y, dependent quantity is v, because that's exactly how it is in your line equation. But when it comes to your x, your independent quantity, it is not exactly how it is in your independent variable. It is the square root of 1 over d squared, or 1 over d. Because remember, the square root of d squared is d. Done. Now, for your objective quantity, we already said this, it is the thing that you're trying to determine, and that is c. And it is always included. Your objective quantity is always included in your slope, okay? Objective quantity c. Then, anything that is constant, like mass, like gravity, like density, are included in your control variables, and they are also going to be a part of your overarching slope. It is not your objective quantity. It is just a part of your slope, like what you're going to have here. So because the slope, just like you have it in your line equation, is equal to the square root of 8 times mass times acceleration due to gravity times pi times c times density. Pi, just in case, pi is a number. It is not, it's not a variable. It is a number. Because it is a number, it was not included in the control variables. Okay? And now the only thing you need to rearrange is the equation, because now your focus is to move everything, solve for c. So you're going to go c equals 8 times mass times gravity times pi times density times the square or slope squared. I literally moved everything from one side to the other because I wanted to have my objective quantity by itself. That is all that I did. That was step 8. And if you get this right, you get the table right. Done. You are done for this section. Congratulations. If you have any other questions, please let me know. Let's go now to the propagation of error, because I know a lot of people are struggling with this. So use the error propagation table and recorded data to calculate the confidence interval for a unitless value. So we have A. This is our whole equation. The objective quantity magnitude is just replugging your measurement values right here back into the equation. So A equals 0.013 times 1.75 over 8 times 0.954. You should get a certain value, and you should have 2 significant figures, at least for now. Because if you look at the slope has 2 significant figures over the rest, which have 3. Always go to the lowest significant figure, and that is the slope, because it's showing you that it only has 2 significant figures. Okay? But now we have to deal with the propagation of error of A. We have 3 different measurements. Remember, we have 3 different measurements. Because we have 3 different measurements, we have to find the partial derivatives of each of those 3 different measurements. So it will go something to this effect. The absolute uncertainty of A is equal to the square root, the partial derivative of A with respect to the slope times the absolute uncertainty of the slope squared plus partial derivative of A with respect to B times the absolute uncertainty of B squared. And finally, my third measurement, the absolute uncertainty of A with respect to C times the the partial derivative of A with respect to C times the absolute uncertainty of C squared. Notice we are given the absolute uncertainties of the slope of B and C. I'm going to write it down. Let's check. Check, check, check. Those are the absolute uncertainties right here. You are given that. Okay? What you're not given right off the bat is the partial derivatives. So let me put it as an example. Let's start with examples. So just to refresh your memory about the derivatives in general. If we have y equals 2x squared, we just do the power rule, right? It would be derivative of y with respect to x is equal to 2 times 2x to the power of 2 minus 1. So I bring this, notice what I did. I bring the 2 down, the original 2 down, and I subtract the 2, the power of 2, by 1. And I'm left with 4x. That's all I did. Okay? Notice that I didn't touch this constant. It is still there. I just multiply. I brought the 2 down. I multiply by 2. And now it is 4x. Okay? Derivatives. Now, let's do something else. Let's say that we have y equals 2x3, that's to the power of 3, minus 1. Again, the same story. The derivative of y with respect to x is equal to 2 times 3, because I brought the 3 down, x to the power of 3 minus 1. And then since 1 is a constant by itself, remember what I said, it is a constant by itself, it goes to 0, and then you have 6 times x to the power of 2. Done. Okay? Now let's say that you have y equals c over x, where c is some constant. That constant could be 4, 5, or whatever. It is just a constant. Then you deriving it, what you do is you bring the x upwards. You take it off from the numerator. And this is just, just certain steps. You bring it off to the numerator. It will be x to the minus 1 because when you're bringing something up from the denominator to numerator, that exponent turns into a negative number. So in this situation, it would be -1. So you're doing the power rule again. So x to the -1 minus 1, remembering that this -1 will be brought down, and that would be -1 right here. And you're left with -1 times x to the -2, or -1 over x to the 2, power of 2. Okay? And one thing that I completely forgot is that we still have a c here, so that is a constant. That c stays. Okay? The c stays right there. It is still a constant. You don't touch it. Okay? Just so you don't get confused. Okay, so now let me erase this. With partial derivatives, the only thing that you should focus on for each partial derivative is the thing that you're deriving at that moment. So when I say the partial derivative of a with respect to the slope, the only thing that you're focused on is the slope. So, in order not to get confused, go slope times b squared over 8 times c. All this is treated as a constant. The only thing that you're going to be focused on is the slope. In this situation, since the slope is to the power of 1, when you're doing the power rule, it goes power 1 minus 1, bringing the 1 down, and this goes to slope to the 0, and slope to the 0 always goes to 1. Remember that. Anything that is to the 0 always goes to 1. So you have left, let me rewrite this. B squared over 8c. Done. Now, you do the same process for each one. And let's do the partial derivative of a with respect to b. Separate everything else except b. So let's go b squared, separate everything else, slope over 8c. Now, this b is the thing that you're focused on. Meanwhile, so the slope over 8c is all treated as a constant, so you just leave it alone, since it's being multiplied by the thing that you're deriving. If this was by itself, where you would be b squared plus slope over 8c, notice the plus, separated, completely separate from the thing that you're deriving, then this, when you derive the slope over 8c, it would go to 0. But since it's multiplied by b squared, it does not. It stays there. And that would be, let's do the derivative of b squared. So b squared minus 1, you bring the 2 down, and you're left with 2b times the slope over 8c. Done. Again, do the same process for the partial derivative of a with respect to c. Separate everything except for, separate everything, separate the 1 over c, and leave everything else to the side. Slope b squared over 8c, and this, again, constant. It is a constant. You don't touch it. The only thing that you're worried about is c. And we talked about this. When it's 1 over c, bring the c upwards, bring this into the numerator, that would be c to the negative 1, and then you apply the power rule, c to the negative 1 minus 1, bring this negative 1 down, that would be negative 1, and what you're left is minus 1 over c squared times slope times b squared over 8. And you're done finding the partial derivatives. The next thing is simply using all your measure values and replugging these measure values in b, in c, and in the slope. You get certain values on that, replug it into your original equation, multiply by your absolute uncertainties, square them, and then square root them, or square them, sum it up, then square root them, and you should get the partial, or not the partial derivative, the absolute uncertainty of A. All you have to do is rewrite this as A plus or minus the absolute uncertainty of A. Remembering significant figures, this is just one significant figure. Okay? And you are done. I hope this was helpful. Please, if you need to go rewatch some of the video, like try to comprehend what happened here. It's like if you're still struggling with derivatives, please let me know. We can go through other mathematical examples to help you remember or refresh your mathematics. Okay, this is the most that we'll ask of you when it comes to like actual mathematics that will count. Okay, so I am here to help. I did this video just so we can clarify some stuff. I'm very happy about this. Let's get it done. Let's get the lab WPR done. I have full faith and confidence that you'll do great. Okay? All right. Have a good day.